So welcome to online video lecture for the subject electrical machines 2, and we are going to continue the session regarding the starting and speed control of induction motor. So that is the part 4 here. So let us discuss the stator resistance or the reactance starter. So in this method, a variable resistor or inductor is connected in series with each phase of the stator winding of a 3-phase squirrel cage induction motor. So this figure, you can see the figure here. This is a circuit diagram there. So for each phase, we have connected a resistance in series to the line. Okay, and of course, these three resistance are variable. Either through some mechanism, we are going to vary this resistance, and it is connected to the stator of the machine. That is the induction motor. Okay, so let us see. So starting, stator resistance itself, meaning itself, we are going to add the in series. We are going to add the resistance at each phase. So what is the purpose of the adding the resistance? Means we are going to regulate the current. So that is the main thing. Okay, and obviously, what happens at each phase, the voltage is also getting varied. Okay, so let us see that ratio. I can call it as the X into V. So where X is some constant or some ratio there. Okay, so that means either if you want to apply 90% or 80% or 70% likewise. Okay, so 100% we are not applying the voltage. Next, very low voltage is applied to each phase of the winding at the start by inserting more resistance or inductance in series with the winding. Okay, so that's what I mean. So especially when we are conducting the in the laboratory test, that is regarding the magnetization characteristics. Likewise, at the generator side, we are going to apply the maximum resistance. So that gradually we are going to apply the rated voltage. We are making to excite the voltage. So we are going to control that. So likewise here also, we are applying a very low voltage at the stator side. So what happens, we'll see. As the motor picks up the speed, the resistance is taken out of the circuit. So that's what happening there. So soon after, initially we are regulating the voltage. That means a low voltage, either maybe at 20% or 30% or 50%. Okay. So slowly at the starting itself, we are applying a low voltage. So soon after, it is trying to reach the rated speed. Then what we are going to do? Gradually, we are going to remove the resistance. Remove the resistance in the sense, either we can bring back to the minimum position, or we can remove the total complete resistance there. By the help of the additional switches, we can bias it. So likewise, let the voltage applied across each phase be reduced to a fraction of X. So we don't know the exact what is the ratio there. So that means either 10%, that means 1/3 or 1/4 or 1/2, likewise. Okay. Next, voltage applied across each phase at start equal to X into V. So you look at this, because all the resistance are same, all will be equally having, equal part of resistance will be added to each phase. Okay, so that is also a balanced condition. Okay, so for at each phase, we are going to add the resistance or the inductance. Okay, so equally to each phase, so that the stator part will be balanced there. So there may be, if not so, if you are not applying the equal resistance at each phase, it may create unbalanced condition. Okay, if it comes to the unbalance, means additional losses will be there, of course. Additional losses along with that, they will exist the negative sequence components. So that is not discussed right now. So that is the main problem with that. If the three-phase system is unbalanced, means there exist the sequence components currents. Okay, right. Next, the starting current. So IST equal to, let us consider as X into ISC. So that is the short circuit current. So as we have gone through all the working principle or how the motor functions, so we came to know that because of the lower resistance part, so at the starting of the machine, when the high inertial loads are connected, so it draws the huge amount of current. So what is that huge amount? How can we term it as the huge current? Means we are rating it, we are terming it as the short circuit current, in which the maximum current is applied in the machine. So we are expecting that the maximum, in the sense the short circuit current. Okay, and that value depends upon the X, because we have regulated the voltage here at each phase. So obviously, what about the current also? It will be X into ISC. Okay, right. Hence, the current is reduced to fraction X. So that is the reason. So initially, if we are not applying any type of resistance and directly we are starting, means we can expect a huge amount of current. That is the short circuit current. So that is the maximum current. So when we are applying, when we are applying in this method, and we are going to add the resistance and we are going to regulate the voltage. So we don't know what is the particular ratio there. If we consider it as an X, obviously the current is also regulated there. So it depends upon the factor X, okay? Or you can term it as K. That's up to you. Okay. So substituting this in the starting torque equation, which we have defined, which we have got equated from the earlier sessions, we can have the proof. So how we got the starting torque equation here, which is equal to full load torque into starting current by full load current whole square into slip wet full load. Okay. So again, all the terms I had not mentioned here. What is TST, TFL, IST, IFL, and SFL? Okay. All these things you have to include this, right? So therefore, the starting torque equal to full load torque into what is the starting current here? So which is IST equal to X into ISC. So this I am going to substitute in this equation. Okay. So this is the term. So this is how we got X into ISC by IFL whole square into SFL. So again, this X, that means this X square, I'm just moving towards it. I mean, bringing to the first position. So that is the starting torque equal to X square into full load torque. So next, higher power factor during starting. Okay. So higher power factor, so that is this point also we have discussed in the previous session. So that means if we add the resistance at the starting itself, so that we can regulate the current, means, so of course the power factor can be improved, but after that it has to be removed there. So we cannot continue the adding we cannot continue the addition of the resistance at each phase, because it may leads to additional losses and obviously the power factor gets reduced. Okay. So that is why they have mentioned that at the starting the power factor will be higher. So soon after reaching the rated speed, or when it reaches the rated parameters, and we need to remove the resistance. If not, there may be chance of, obviously there will be increase of losses. Okay. So that should not happen. After that, we need to remove this resistance or inductance, whatever we have connected. Next, coming to the demerits of this method. So current is reduced by a fraction of X, but the torque is reduced to fraction X square. Hence, starting torque is poor. Okay. So this is obtained from this, look at this equation. So TSA, starting torque equal to X square there. So let us consider this term is nothing but depends upon the voltage, right? See, look at this diagram. If you are going to regulate the voltage, means what happens? As in the previous sessions we have discussed, torque is proportional to E2 square, right? If the supply voltage is constant, it will be obviously equal to V. So then the equation becomes T is proportional to V square. Okay. So that means if you are reducing the voltage, so what happens? Obviously, the torque also gets reduced. Okay. So torque is also reduced, means what happens? So it, see, so torque is reduced means what happens? It takes some time to reach the maximum torque during the process of reaching the rated speed. Okay. Next, more energy loss in the resistors. Therefore, inductors are preferred, but still loss is more. Okay. So as I said you, we are going to regulate the current, means what happens? Uh, through, if we are preferring a resistors instead of the inductors, the energy dissipated is in the form of heat there. But if we prefer in case of the inductor, okay, so for at each phase, see, look at here, at each phase, we can, if we prefer an inductors, so what happens? Of course, the inductor has the property, what is that? It can avoid the inrush of currents. Okay. But anyhow, the losses will be there even if you prefer resistor also, but the cost will be higher. So that is why they obviously prefer the resistance, and it is more feasible. Okay, next, starting duration is comparatively more. Okay, starting duration, as I said you before. So this duration, so what is the duration means? We need to run the machine at its rated parameters. So that means either rated speed or when it reaches the rated current, likewise. Okay, so this duration will be more in this method. So that is the one of the main drawback. So that is why we are using this method rarely. Okay, next we'll discuss the star delta startup. So this method is based upon the principle that in star connections, voltage across each winding is phase voltage, that is 1 by root 3 times the line voltage. Whereas the same winding when connected in delta will have full line voltage across it. Okay, so this is the fundamental thing, that is the voltage equations in the star connection and the delta connection, right? So what is the line voltage there? So that is 1 by root 3 times. So whereas in delta it is root 3. So based on those, based upon that fundamental thing, we are going to use that, and we are going to regulate the speed. So let us see how it is. Okay. So at start, connections of the motor are made in star fashion. Okay. So that the reduced voltage is applied across each winding. Okay. After the motor attains speed, the same windings through a changeover switch, as shown in figure, are connected in delta across the same supply. Okay, so let us see here. See, before going to the circuit diagram, so you must know what is a changeover switch. So this is the of course this is a changeover knife switch. Even it can be, now they are using the like an MCB also. The changeover switches are manufactured like that. But to know what is internally happening, I have used this figure. Okay, so this is manually pushed or pulled there. Okay, so this is one this gives one set of connections, that is if star connected windings are there, then we are going to push here, or if we want to connect at the delta, we need to pull here. So by using this this bar here, this plunger. Okay, so here the pulling and pushing action are performed. So this is nothing but a changeover switch. Okay, if it is in the middle portion, means there is no connection there. Okay, so you can see here it appears to be a knife there. You can see the tappings here. So RYB neutral. Okay, so this is nothing but a changeover switch. Okay, so here there will be supply, and here also there will be supply there. Okay, so sorry, here this is the breaking point there. So these are the breaking points. This gives the one set of connections, and this gives the another set of connections, and we are going to tap it based upon our requirement. So this is nothing but a changeover knife switch. Okay, right, we'll see the thing. See what, once again we'll recall what they have done. At the start, we are going to connect the star connected winding. Okay, after motor reaching the rated speed, or when it reaches the final value, okay, then we are going, with the help of the changeover switch, we are connecting it to the delta. So simple thing. So only two cases. At the start, we are going to connect the machine with the star connection, and after that, when it reaches the rated speed, or when it reaches the final value, it is connected to the delta connection with the changeover switch. Okay, so let us see the procedure here. Okay, see, so this is the supply mains, and this is the main switch. Okay, so this may be an MCB also. So look at these tappings are there. So simplified diagram, first of all you see the simplified diagram here. So this is the knife switch. So based upon our movement, based upon the action, it will be tapped at the these terminals or these terminals. Okay, so if you want to connect the star connection, so what is the case there? See, here you can see the start position. So start in the sense it should be in star connection. Okay, at the starting we are going to connect in star fashion. Okay, see, let us see. if we consider it as an RYB phase, so if it is an R phase, okay, so this is between, so here it is ended, so between 1, 2, through this, here it is connected, here it is, all these are shorted there, okay, and if it is connected to the neutral, 2, 4, 6 are shorted here, you can see there, okay, but whereas coming to the run position, 2, 4, 6 are not shorted, all these are separately connected, okay, so this gives the star connection. You can see the representation, I hope you can understand this. See, 2, 4, 6 are shorted and it is connected to neutral, means it is a star connection, okay, other than that it is an delta connected. See here, look at here, 1, 2, so again it is given to the, see you can see there again some 5, 6, and again, so this is the connection. Here you can analyze, so 1 here, again it is going to 3, 3, 5, then 6, 4, 2, all are shorted, okay, here 6, 4, 2 are shorted and it is connected to the neutral, so this is the connections. So this is nothing but a changeover switch. Of course we are using the here overload and no volt release coil, so don't focus on these two relays. So all the points we need to all the points we need to discuss, or we need to highlight regarding the changeover. So how we are connecting the star connection, how we are connecting the delta fashion, okay. So here the stator winding, in the sense it will be, all the phases will be having the tunnels there, so you can see the tunnel box as we have seen in the construction details of the induction motor. There you can see the tunnel box there, all the phases and the starting and the ending end will be tapped there, and we can see the tunnels, okay. So accordingly, with the help of the changeover switch, we are going to tap the connections, okay. So if if it is in downward direction, see if we have pull it here, so that means if you have pull it towards our side, then it gives the star connection, okay. If it is in opposite direction, then it is delta connected, okay. Okay, here you can no need to give the current direction and all, but you can simply use these two diagrams, simplified diagram, okay. So only the stator part we need to focus, how it is connected in the star and how it is connected in delta, so that itself is enough, okay. So overload and no volt release coil already have explained in the previous sessions, how this overload relay will conduct, how this no volt relay will conduct, okay. So this is also interface to this changeover, this no volt release coil, okay, right. Let's see the procedure. See, the starter is provided with overload and under voltage protection devices also. So that is mentioned here. So this is the no volt release coil, and this is the overload release coil or overload relay. Okay, next. Moreover, the starter is also provided with a mechanical interlocking, which prevents the handle to put in run position first. So mechanical interlocking, in the sense, so see, this is the case. See, this is the mechanical interlocking there. So that means if we provide any action there, it has to lock there. I mean, the switch has to be locked. See, you can see the figure here. So if we press the, if this knife is inserted here, it is going to lock there. So there's some mechanical force, I mean mechanical action will be there, such that it can hold the switch or it can hold the contactor. Okay, so there we are not going to perform any magnetic force or any magnetic field there, we are not utilizing. Actually, based upon the mechanical force there, so it is going to hold the position. Okay, right. Next, since at start stator windings are connected in star connection, so voltage across each phase winding is reduced to 1 by root 3 of the line voltage. Okay, so there we are not doing any control method there, so directly just by using the changeover switch we are connecting in star connection. So what happens in star, the line voltage is equal to, so 1 by root 3 times. Okay, so therefore starting current or phase becomes ISC by root 3, which is the starting line current. Okay, so whereas starting line current by direct switching with stator winding is connected in delta is root 3 into ISC. So if, without using any changeover switch, if we directly connect the machine which is of delta connected, means what is the value there? It is root 3 times of the short circuit current. Okay, right. So now equate these two things. I mean, take the ratio here. So line current with star delta starter equal to ISC by root 3. Line current with the direct switching equal to root 3 into ISC. So what is the final value there? So it is 1 by third times, 1 by 3 times. Okay. Thus it includes that when a three-phase motor is started by a star delta starter, the current drawn by it's limited to 1/3 of the value that it would draw without a starter. Okay, so there we have seen the DOL starter. Okay, some other starters there we require additional devices there, but with the help of a simple changeover switch we can limit the starting current. So how much extent we can limit means it is 1/3 of the short circuit current. Okay, next, torque developed by the motor when started by star delta starter. So the same thing. So by using these current equations, and we are going to substitute in this starting torque equation the same thing. So we substitute the starting current here, that is IST by root 3. So how it becomes? So TST equal to 1 by 3 into, so this is 1 by 3, so root gets cancelled here, it becomes 1 by 3 TFL ISC. So what is IST here? So this is IST, starting current, starting line current. Okay, that is ISC by root 3. So ISC by IFL whole square into SFL. Again here TST is the starting torque, TFL is the full load torque, ISC is the short circuit current, IFL is the full load current, and SFL is the full load slip. So from this torque equation, what we are going to conclude means the starting torque in this what is this method? That is star delta starter. In the star delta starter, the torque equation is equal to 1 by 3 of the torque developed by direct switching. Okay, instead of directly switching the machine, of course, which is not encouraged, that there may be increase of short circuit current. So that if you use this method, we can limit the torque to 1 by 3 times of the torque developed by direct switching. Okay, so this equation shows that the starting torque developed by the motor when started by star delta starter is also reduced to 1/3 of the starting torque developed by DOL switching. Okay, so that is the one more advantage of using this method. Okay, next let's see the what are the merits and demerits here. It is a simple, cheap, and effective and most efficient method of starting of squirrel cage motors, and it is the most suitable method of starting for high inertia and long acceleration loads. Okay, so long acceleration in the sense, uh, I mean some type of machines which is especially used in industries, it has a long period of acceleration. That means the either increase or decrease. Okay, I mean it can withstand the variations there. Okay, so in that particular type of machines, we can use this method. And there are some certain demerits. Let us see. All the 6 terminals of the stator winding are brought out to starter through 6 leads, and the motor has to be operated in delta. So all the 6 terminals in the sense we can see here. So this is 1, 2. So 6 terminals are there. So that is 1, 3, 5, and 4, 6, 2. So that is the case. Next, starting torque developed by the motor is reduced to 1/3, which is very low to pick up the load. So as I said, you obviously if the torque is, I mean the starting current is limited here, so which will reflect on the voltage also. I mean because of this voltage only the current is limited there actually. So look at here, it is a VL by 1 by root 3 times of the 1 by root 3 terms of the line voltage. So there what happened? The voltage is regulated. Now if voltage is regulated means obviously again there is effect on the torque because T is proportional to V square. Okay, next. So accordingly, such starters are employed with squirrel cage induction motors having capacity 4 kilowatts to 20 kilowatts. So between these ranges of the machine, we can use this method. So coming to the last type of the method, that is the last starter there, auto transformer starter. So this is mostly we can see in the laboratory purposes, laboratory testing also you can see by using a either in case of the single phase we are using single phase variac or the single phase transformer, and coming to the three phase there also we are using the three phase transformers. Okay, right. So in the previous method the current can only be reduced to 1 by 3 times the short circuit current. Okay, so that is as per the final statement. So this is the statement there. Okay, next. Whereas in this method, the voltage applied across the motor, and hence, in this method, the voltage is applied across the motor, and hence, current can be reduced to a very low value at the time of start. Let us see how we are going to apply the full voltage, and we are going to reduce the current only itself. Okay, let us see. At the time of start, the motor is connected to supply through auto transformer by a 6-pole double throw switch. Okay, so it is also nothing but a changeover switch. Okay, when the motor is accelerated to about full speed, the operating handle is moved to run position. Okay, so by this motor is directly connected to the line as shown in figure. So look at here. Here also we are using the changeover switch. So here actually what happening in the sense. This first of all, look at here how the circuit configuration is. Here we are using a main switch. Okay, so directly we can give the supply to the machine. I mean that is the stator winding, but that is not happening there. With the help of the auto transformer, we are going to give certain percentage. That is, 50% or 20% tapping or 80% tapping or 75% tapping likewise. So initially we are going to fix the tapping and we are going to start the machine. With the help of this changeover switch, we are going to give the position at start. Soon after reaching the machine to a rated parameters, then we are going to use this change by using this changeover switch. We are going to tap to the run position. So run position means directly the supply is given to the machine. There is no control of any voltage or there. So during with this process, what happens means at the starting we are going to limit the current by using these inductors. These inductors. That is, of course, it is also a inductors connected in each phase. So it is nothing but a transformer, auto transformer there. With certain tap ratio, we are going to give the supply to the machine, and soon after reaching the rated parameters, we are going to supply the full voltage. So soon after reaching the rated parameters means it is not a big issue when we provide a full voltage there. So this is how we are going to limit the current, and we are going to start the machine. So this is also one of the efficient methods. Okay, as explained is earlier in this method also we use overload protection and under voltage protection there. That is by default for all the methods. Next, although this type of starter is expensive, but is most suitable for both the star connected and delta connected induction motors. It is most suitable for starting of large motors, as I said you before. So this is the by using auto transformer, it is one of the best suitable for the high rating machines. And large size motors draw huge amount of current from these mains if they are connected to mains without starter. So as I said you, if we are preferring the high rated machines means what happens? Obviously the short circuit current for that machine also will be very higher, and we need to limit that. So if you want to limit that, we can use this method. So that means by using a auto transformer, we are going to regulate the current, and soon after reaching the rated parameters, rated speed, we can tap it to the full line voltage. Okay, next. However, if they are connected to the mains through star or delta starter, the current is limited to 1/3 value, which is still so large that it would disturb the other loads connected to the same line. So the problem is that if we prefer a high rating machines means with this any variations in the line, okay, if it is 1/3 or a 1/5 times likewise, so it is going to disturb the other connected parallel loads. In the previous session also I have said you, if all the machines are connected to the transmission lines there, if any variations in one load, that means in one machine, it is obviously going to disturb the other machines also. It causes the variations in the line also. Okay, hence to limit the initial rush of current to low values, auto transformer starters are employed there. So here also we will see the equations. See how the starting torque is regulated. So obviously here also the motor started by an auto transformer having ratio K. So what is the percentage? We can treat it as a K. Okay, and applied voltage to a stator is K into V. and the starting current ist equal to k into isc, because it depends upon the ratio k. If k equal to 1 means obviously ist equal to isc. Then the supply current equal to k into secondary current of transformer, that is k into isc, which is equal to k square isc. Again substituting this k square isc in this starting current equation, that is the torque equation. So we get starting torque equal to tfl into k square isc by ifl whole square into s into fl. Okay, sorry, sfl. So starting torque equal to k square into torque developed by direct switching. So which is relevant to the resistance method, right? So there also we have seen starting torque equal to x square into torque developed by switching. That is we have seen in the resistance method. Similarly here also we have considered the same ratio. Here we have termed it as k. So this is the best suitable method, and we have considered one small example that one if 20%, if the ratio k is 20%, so it will be 1 by 25 times. Okay, so it depend, I mean based upon the voltage we are regulating, obviously the current is also depending there. So that's all about the starting methods of three phase induction motors. Hope you have understood this session. So thank you.